Spider-Man's webs are amazing. They can be stretched, pulled, and hold tons of strength without breaking. Additionally, they're waterproof, making for arguably the best single tool a superhero has ever had. But how? I mean, what is this spider web made of? This isn't answered by the comics or movies. The closest thing, and correct me if I'm wrong, to seeing any sort of creation was in Spider-Man Homecoming, where Peter is seen making a fluid in his chemistry class. So let's scratch that idea. Instead, since Peter was bit by a spider, let's assume he would model the web fluid he uses after real spider silk. I mean, it all makes sense. Peter was bit by a spider, and therefore the material that would work best for him would be actual spider silk. Also, it makes a story of a high schooler making this insane web fluid a tad bit more believable. Anyway, let's first take a look at the biological makeup of why spider silk is a perfect fit for Spider-Man, and then let's look at how much force this material can actually take. So first, what are actual spiders' webs made of? Well, an actual spider web is made of proteins called spidroins. Spidroins are a type of protein that spiders produce in their silk glands. These proteins are composed of long chains of amino acids. The structure of spidroins are what gives spider silk its remarkable strength, flexibility, and hydrophobic properties. So to understand this, we need to understand how proteins are folded. And this starts with set amino acids. The polarity and charge of each amino acid dictate how a protein folds. There are amino acids with positive and negative charges which attract to each other. There are also polar amino acids which face the outside to bond with water molecules, and non-polar amino acids that stay in the core to stay away from water. This folding process is crucial because how a protein folds dictates its function. In the case of spidroins, the folding results in a combination of crystalline and amorphous regions within the silk fiber. So let's break down each level of folding for proteins, as well as see how these are represented for the spidroin protein. First up is primary structure. This is just a simple order of amino acids held together by peptide bonds. This is the sequence of amino acids in the spidroin polypeptide chain. The specific order of amino acids determines how the protein will fold. Next up is secondary structure. These are loops and folds held together by hydrogen bonds and hydrophobic and electrostatic interactions in either beta sheets or alpha helixes. In spidroins, the secondary structure consists of beta sheets. These are formed by the hydrogen bonds between the backbone atoms in the polypeptide chain, leading to the formation of rigid planar structures. These give the silk its strength. The amorphous regions, on the other hand, are more disordered and provide elasticity and flexibility to the silk. Next up is tertiary structure, which is just the overall three-dimensional shape of the spidroin molecule, which includes the arrangement of the beta sheets and other structures within the protein. The tertiary structure is stabilized by interactions between the side chains of the amino acids, such as hydrophobic interactions, hydrogen bonds, and ionic bonds. Finally is quaternary structure. This is multiple tertiary folded chains clumped together. In spider silk, multiple spidroin molecules align and pack together to create the long, strong fibers characteristic of spider silk. Now, one of the more remarkable properties of spider silk is that it is almost hydrophobic. This is again largely due to the spidroin's specific arrangement and types of amino acids. The non-polar hydrophobic amino acids are typically buried within the core of the protein structure, while the polar hydrophilic amino acids are exposed to the surface. When these polar amino acids are exposed on the surface of the protein, they interact with water, but in a very controlled way that helps maintain the integrity of the silk structure. This arrangement minimizes the interaction with water, making the silk somewhat water resistant. But again, because the outside of the protein is still hydrophilic, it can still interact with water. I guess that's why Spider-Man's webs dissolve after a while. Additionally, it is important to point out that spiders produce different kinds of silk for various purposes. For example, there's dragline silk, used for this web's framework and as a lifeline for the spider. It is incredibly strong and tough. Next is tubuliform silk, used to make egg sacs, providing protection for spider eggs. Next is aciniform silk, used to wrap and secure prey as well as to reinforce the web. Finally is flagelliform silk. This type of silk is very stretchy and is used in the capture spiral of the web to absorb the impact of flying prey. Now let's move on to figuring out how much force these webs can actually take. To figure this out, I'm splitting the process into 3 steps. First, we'll use kinetic and potential energy to determine Spider-Man's speed during a fall. To really test the web's strength, we're going to have Spider-Man fall from the Empire State Building and catch himself on the web at the last second. Once we find the speed, we'll use that in the centripetal force equation to calculate the tension force on the web. First, we need to find out how fast Spider-Man is going right before he uses his web. So first, let's take a look at the blueprint for the Empire State Building. The building itself is 1,454 feet tall. So in the game Spider-Man Miles Morales, I took Spider-Man up the building and let him fall. Just before he was about to hit the ground, I had him swing. In this scenario, Spider-Man's movement is similar to a pendulum. When he falls, he starts at an angle, and when he swings back up, he's moving in a circular path. When he first uses his web, he has both potential energy and kinetic energy. Potential energy is stored energy. An object has the potential to do something, and there's energy associated with that. It is given by potential energy equals mass times acceleration due to gravity times height. Kinetic energy is the energy an object has due to its motion. It is represented by kinetic energy equals 1/2 mass times velocity squared. As Spider-Man reaches the lowest point of his swing, his potential energy is minimized, but it isn't zero. He still has both KE and PE. But if we subtract the height of the tower and the height at his lowest point in the swing, then we can say that his lowest point is at h equals 0, or the height is 0. This makes it really easy for our further calculations. This is because at the lowest point, when height equals 0, that means there is no potential energy, and that means there's only kinetic energy at that point. As you see, Spider-Man grabs his web at the height of a lamppost, around 27 feet and 7 inches. So we subtract that height from the Empire State so that the new height he fell is 1,426 feet and 5 inches. Now, since Spider-Man only has kinetic energy at this point, we can calculate his velocity to use for later in our centripetal force equation. Let's rewind a bit back to when the web is first cast. At that moment, Spider-Man has both potential and kinetic energy, and the total mechanical energy is the sum of the two. Therefore, mechanical energy is potential energy plus kinetic energy, or mgh plus 1/2 mv squared. The mass, height, and acceleration due to gravity are constants we can plug in. The height in this case is the height from the ground, and not to be confused with the height Spider-Man fell. The height Spider-Man fell will be instead used to find the velocity in this case. To find the velocity, we can use one of the uniformly accelerated motion equations. This equation allows us to solve for velocity squared without needing the time variable, which is very helpful. There's also an initial velocity term, v squared naught, but I'll ignore it for simplicity. Spider-Man having a slight initial speed won't change the calculations much. So let's just get on to solving for velocity squared. First, I plug in the acceleration to the gravity, as well as the height that we solved for earlier. Then I multiply both of them by 2, and I get v squared is equal to 8,528.8 meters squared over seconds squared. Then I insert that back into our original ME equation, which gives us a final mechanical energy of 541,579.2 joules. Now here comes the amazing part. Spider-Man will now swing to the lowest point where he only has kinetic energy. And since energy is conserved, the mechanical energy we calculated earlier equals the kinetic energy at this point. Therefore, 1/2 mv squared equals me. We solve for v squared here to find his speed at the lowest point of the swing. So v squared now equals 17,057.6 meters squared over seconds squared. Once we have this number, we can finally move on to our net force calculation using centripetal force. It's important to point out that centripetal force isn't an actual force. It's the net force that keeps an object moving in a circle. In this case, it's the combination of the tension force in the web holding Spider-Man up and the gravitational force pulling him down. Centripetal force always points to the center, and to keep Spider-Man moving in a circle, the tension force has to be greater than the gravitational force. So our equation is centripetal force equals tension plus gravitational force. This is where our velocity calculation comes in handy. You see, centripetal force equals mass times centripetal acceleration, and centripetal acceleration equals v squared over r. The v squared is what we solved for earlier, and r is just the radius of the web, or just the distance from Spider-Man's hand to where the web starts. We can find r by using the period of the pendulum equation. The period of the pendulum equation is that period of a pendulum equals 2 pi times the square root of r over g. The way I found the period of the pendulum is by slowing down and measuring the time it took for Spider-Man to swing. You see, Spider-Man only swings 1/4 the distance of a whole period. So what I did was take that number and multiply it by 4. Now that would be our period of a pendulum. Now let's just set that equal to 2 pi times root r over g and solve for r. Therefore, r is 2.63 meters. Now we can take our 2.63 meters and solve for centripetal acceleration, which is 6,485 meters per second squared. Now we can just solve for Fg, which is just m times g. So now our new equation is mass times centripetal acceleration is equal to T plus mg. Now we can just plug and chug to solve for T, the tension force in the web pulling Spider-Man. Wow, that is a huge number. And again, this total could be even higher. If the radius of the swing was shorter, the acceleration would be greater, making the tension force even higher. But this just gives us a rough estimate of what Spider-Man's webs are really capable of. Anyway, thank you guys so much for watching this video. I hope you really learned some awesome physics and biology about Spider-Man's webs. Sorry this video took so long to get out. Hoping to get one out by this Saturday, so stay tuned for that. Anyway, subscribe, comment down below what you want to see us do next, and yeah, peace!